I'll start with the shout outs to the community first again. So yeah, we had a couple of newcomers to the forum, several people who introduced themselves. So just, yeah, thanks for everyone who introduced themselves. There's a researcher, computer science student from Korea, asking a question about spiking neural networks, how that relates to what we're doing. There was Adam, who introduced himself, starting an indie game company. He also wrote some nice other posts on the forum that I'll highlight in a bit. Afner, who also introduced himself, asking a question about LLMs in Monty and or potentially combining them. And then Sujit from India, an AI engineer. So yeah, lots of people interested and kind of joining the forum. And most of them posted some other interesting threads as well. Another few first-time posts. Here was one who shared the YouTube video from Artem Gitanov about the Thousand Brains theory. There was someone who posted some thoughts on the theory presented in the hierarchy paper. This is a recent post from, I think, this weekend. Didn't have a chance to reply to yet, but about a paper about a hierarchical reasoning model that was recently released and how that relates to our work. And then this is Angsten, who also submitted some PRs this month, who's been also posting interesting question around voting and whether there could be additional information in the votes that Niels posted some replies to, and generally around the CMP and what can be contained in it. Yeah, interesting questions. There were several interesting questions around the theory, especially now that we published the hierarchy paper. So here's a question from Trung Duan about whether it makes sense to think more about natural objects versus man-made objects because they are more complex, and how that might give us some useful perspectives. There's a long back and forth post about the purpose of lateralization in the brain, why we have left and right hemispheres, if that has any specific functional purpose.
Hey, before you go on, Vivian,
Yeah.
I think that the post in the upper left there from Chung Dong, that's an interesting question, and we should think about that some more. I mean, we might be fine with the way we are doing things now, but the idea that sort of ill-formed boundaries is something we have to deal with, and we might be doing fine with that. I don't know, but it's worth at least acknowledging that.
Yeah.
I thought it was a good question.
Yeah, definitely. I was actually thinking about that today, about like whether man-made objects are so simplistic, whether that says something about the kind of models we're learning in our brains. But yeah, definitely.
I mean, it gets back to the question we've had many times, is like, oh, a tree doesn't have a very clearly defined morphology, but they have some morphology, and how do we deal with that here? All right, I just wanted to shout out. That was a great question.
Yeah, I agree. Thanks. There was a nice detailed post from Adam about some ideas on how the API of Monty could be changed to make it more easy to use. Kind of, yeah, as an outsider's perspective, someone getting started with Monty on what could be useful. And yeah, Tristan posted some nice replies on it. And we're incorporating any feedback from the community into our roadmap for making Monty more usable. Then we had several PRs from the community as well. Here was one to, a small refactor, dynamically collecting experiment data classes. Then there was one from Angsten about eliminating some NumPy warnings. And another one from Angshan for improving the buffer channel selection logic, which previously was kind of hard coding some specific sensor naming, kind of assuming that the sensor was named patch or had patch in the name. Now it doesn't do that anymore, which is good, making it more general. There was another blog post, I don't know if you remember, Greg Robinson wrote 2 blog posts last month, and this month he posted another blog post, which was a nice read about how from the perspective of the idea of voting, how that could be applied to how psychedelics work. I'm not sure whether the idea is correct or will be validated, but it was an interesting read and fun picture, I thought. And then, yeah, Artem Kisanoff shared this really, really nice video about the thousand brains theory and generally the canonical microcircuit and cortical columns with lots of great animations. And then, given the 2 paper releases, we had lots of interactions with researchers on social media. Maybe one to particularly highlight was an exchange between Niels and Andrew Davison, who works a lot with SLAM and kind of the idea of using structured models and reference frames and generalizing that idea more to objects. So there was an interesting exchange there. And then, yeah, many people shared our papers, for example, Subutai, also many people on our team, of course. So thank you guys for doing that. And then several people kind of sending us some shout outs, like tagging us in posts that they wrote or tagging us with papers that they found that seem to validate the thousand brains theory. Another kind of paper tag on a paper that didn't find any evidence for predictive coding or the kind of predictive coding framework. And yeah, asking how that matches with the thousand brains theory. Just some kind of nice comments on the animation video, on our paper videos and the context around it. Some excitement about, yeah, different way of thinking about hierarchy or heterarchy in the neocortex. And then, yeah, Bruno Sanchez also shared or tagged our project several times on LinkedIn in different posts about energy efficient AI and exciting new approach to AI. So yeah, thanks for everyone who shared our project and tagged our project or even contributed to our code.
So yeah, really exciting today. We've got 2 topics. First one, Ramy's going to be presenting some of the work he's been doing recently on kind of a key stepping stone getting us towards compositional objects. So I think that'll be really interesting. And then depending on how much time we have at the end, we're going to talk about some of the changes we're thinking about making in the code, reflecting some changes we've had on the conceptual side in terms of kind of model-free, model-based policies coming together and how that's orchestrated in sort of something like a subcortical structure. And that's something that kind of Scott will kind of take the lead on. But yeah, Ramy, do you want to start?
Just I throw in, if we have time at the end, I have some thoughts about how we start tackling sort of the broader picture of complex goal-oriented behaviors.
Okay, nice. I mean, that sounds relevant.
Yeah, it's just an idea about how going about it. So
cool.
Yeah, I think we'll have a lot of time at the end. It's the presentation is a little short.
Famous last words.
Yeah, I feel like presentations are never short.
I
if they're open to discussion.
Okay, so so this is hypothesis resampling, and I'm just going to start with the motivation here. And the motivation for this is because we're starting to tackle compositional object recognition. Before, we just had one object in one episode, and we're just trying to figure out what that object is. Now we have, or we're starting to enable compositional object recognition, and there are some changes that we have to do in the code. and one of those changes is figuring out how to deal with multiple objects in the same episode. And I'll explain what I mean by that. But
Can I ask a question already, Ramy? Sorry.
sure.
You say recognition. I mean, we have to learn compositional objects, and we have to infer compositional objects and predict compositional objects, predict components. Is this about all of those, or is it? Or I'm not sure what compositional object recognition is. That seems a broad term.
This is mostly about inference and not
So
learning.
what inferring? I'm inferring a cup that with a logo. It's sort of differently than just a cup. Is that the way to view that?
So a cup with the logo, the lower level LM is going to be recognizing a logo, and then the higher level is going to be recognizing the cup with the logo at the same time.
But this is more the motivation for what Ramy's been working on. So basically what he's been working on is basically only the lower level. So you just have the lower level model, and you can recognize the individual child objects, and you can move your sensor from one child object to another and switch your hypothesis.
Okay, well, that's just object inference. You know, that's right. That's just basic object, multiple objects.
Yeah, it's basically improving object inference as a stepping stone to enable compositional objects. So right now there's no kind of results or anything with compositional objects, but compositional objects would be impossible with how Monty currently is.
All right. Well, it's worth going into this a bit, because when you say compositional object recognition, you have two learning modules or two regions. One is recognizing a mug, and one was recognizing the logo. And so both of those are just standard, what we've done already.
Right.
And so it's really a matter of learning the composition. And then if you're going to say compositional object recognition, it's defining like, oh, this is the mug with the logo, which is different than the mug with, the mug with, something else on it. Okay.
Yeah.
That's what you mean.
If you want to recognize the cup, the cup that has child objects on it, the lower level LM is going to have to switch between objects, and that's something.
All right. Okay. Yeah.
So yeah, this is just what I was saying. Even though we have collocated receptive fields, the higher level LM is trying to recognize this one object, but the lower level LM is just moving between objects to be able to give it different object IDs. And the problem with that is there are some. It's basically in the code base we just have some difficulties with some of the assumptions around how Monty experiment is structured. And I'm just going to go through these assumptions basically, just to give an overview. In Monty, we have an experiment, and this experiment is split into episodes. Every episode is a different object. And we have this assumption that we have a single object per episode. It's coded in such a way that at the beginning of every episode, there is an explicit reset signal that resets everything, basically deletes all of the hypotheses that we had, and it reinitializes a new hypothesis space. This is what it looks like. So at the beginning of every episode, there's a very important step where we use the first sensory observation to initialize a hypothesis space, and then we use that hypothesis space for the rest of the episode. And then after the episode ends, we reset that hypothesis space. And this actually has enabled us to parallelize these episodes and do a lot of very interesting things. But yeah, every episode is very independent. And yeah, like I said, there's too much reliance on the first observation at the moment in Monty, because that's what we use to initialize the hypothesis space. And after that, the hypothesis space is fixed. We're just updating the evidence scores in here. So if the object has changed, even if the object, so if we replace the object with something else, or like if the sensor moves onto another object, or the object is swapped, that first observation is not valid anymore. And so this is the current problem. And like I said, with compositional objects, we want to be able to move between objects in the same episode. So the first thing that we started with is define a benchmark so that we can measure our performance against that benchmark. And the benchmark is very simple. We just define an experiment where we have all these episodes, but we just remove the reset signal in between. So whatever first observation that we come up with here, that's going to be used for all of the episodes. And we started looking at what kind of results that would give us. So what I'm showing here is the maximum evidence score for, like, this is the best hypothesis that we have for just recognition. And on the top here, I'm showing which episodes I'm basically I'm giving to Monty. So like the first one is zoom in a little bit. First one is the mustard is a strawberry, and then a banana, and then the Spam can, or the potted meat can. As you can see, it does very well, or reasonably well, on the strawberry, because this is the hypothesis space that we initialized was based on an observation that was on the strawberry, and it accumulated enough evidence there to be able to confidently recognize it. But then as soon as we started giving it a different object using, and it's starting to recognize using the invalid hypothesis, it cannot accumulate much evidence on those. And it's just, all of the hypotheses are just decrementing in evidence. This is
So that's not good, right?
Yeah, I was gonna say this is what we were expecting to happen. Like, this is not a surprise, but this is just kind of the benchmark showing that, as we expected, Monty in its original version cannot handle this.
And that's what Ramy solved.
Okay.
That's what. So originally, what we would have is just a reset signal here, so that we can initialize a new hypothesis. This is a different view of what's happening. We're defining a different metric here called theoretical limit, which is basically just using the ground truth. We know exactly how the object is oriented and everything. We just look at the best hypothesis that we have based on that pose error, and we just define what is the limit of Monty, basically. If Monty were to choose the best hypothesis, what would be the pose error? And you can see that as it switches, here the pose error jumps, and that is because it basically is using its old hypotheses, and they cannot really work well with the new hypothesis, with the new object.
Does that metric make sense to everyone? Because I feel like it's, yeah, a bit of a
No, I didn't follow it.
So it's like, if you imagine when you initialize, you have kind of a set of hypotheses. Those are, the nice thing about Monty is those are all informed by that observation. So like, if I feel a surface here, then, you know, one of my hypotheses is the mug like this, but also a mug on its side and stuff like that. So that's the set of hypotheses that are initialized. And basically, some of those, all of those, even if they're good, like valid or not, they will all have a distance to the ground truth rotation, like how close they are to the real rotation of the mug, which we can measure. And then we can look at, across all the hypotheses, what is the hypothesis that is closest to the ground truth, even if it has like no evidence for it. Like even if Monty hasn't had a chance yet to explore, and so that hypothesis might not have much evidence for it. But if Monty was to pick it, it would be the best hypothesis of all the ones that it could pick. So that's why it's kind of the theoretical limit, because it's not guaranteed that Monty will select that hypothesis, but by existing, it's in the space of possible hypotheses that could accumulate evidence. And so the theoretical limit is like, what is the lowest one of all? So at the start here, what do you call it? Like it'll be constant in these cases when we change the object. But so as we kind of expect with the first object, we initialize our hypothesis space based on that first observation. So the theoretical limit is good. But once we change to another object, the hypothesis space for that other object was initialized based on a totally different observation that had nothing to do with the actual existence of that object. So none of them fit the real existence of that object particularly well. So the theoretical limit kind of jumps up around step 50.
Yeah.
Okay.
So like, even if Monty would do perfectly on the second object, it just has no chance of getting the correct orientation because it's not in its hypothesis space.
I think I got the basic idea. Maybe.
Yeah. Yeah, so hypothesis resampling is just this idea of that we don't really need to rely too much on the first hypothesis. Instead, at every step, we're going to be resampling some new hypothesis based on the new observation, every observation that we get. And then we also don't want the hypothesis space to explode in terms of its size. So we're also deleting some of the hypotheses that have not accumulated evidence in a while. So the first step is just basically look at the new observation. So we assume that we already have a hypothesis space that has been initialized, and then we just look at the new observation, and then we initialize a few more hypotheses and add them to the hypothesis space. Just one little detail here is that we're prioritizing graph nodes that match with the feature that we're seeing. So because we're not going to sample the full hypothesis space, we're not at every step, we're not really sampling all of the hypotheses that could be sampled, that could be generated, but we're sampling some of them, and we're prioritizing those based on the graph node features. So we're using those features to do that. And then the next step of this would be removing the hypothesis from the hypothesis space. And we do that. So the original thinking of doing that, or a naive way of doing that, would be to just look at low hypotheses that have low evidence scores and just delete them. But that really is not going to work very well, because you may have, once you switch from an object to another, you will have some hypotheses that have very high evidence for the previous object, and those will continue to stay. We're not going to be able to delete them. So the idea here is to remove based on the slope of the evidence accumulation rather than the actual evidence, the absolute evidence values. So we'll be able to just track this slope and just delete the ones that we don't need. So over time, it's like we're refining the hypothesis space over time, rather than keeping a fixed hypothesis space that is tied to the first object that we had. Just one note here, we also had an idea of resampling based on something called offspring hypothesis that is based on the evidence scores. So we would, at every step, we would look at which hypothesis had the highest evidence scores, and then we would resample offspring hypotheses based on those hypotheses. It was something like we would sample from the distribution of those high evidence hypotheses, something like very close to it, which is like we take this one, which is like high evidence, and we just sample something like close to it. And that is just the goal of this is just to fine tune or like closely refine the hypothesis space so that it goes towards better and better theoretical limit.
And it's kind of informed by, or like one of the inspirations is the particle filter approach that's often used in like SLAM techniques. And the advantage is that you can start out with a pretty sparse sampling of the possible hypothesis space, but then once you have kind of a certain location and orientation becomes more and more likely, you can sample similar locations and orientations to refine your estimate and make a very exact prediction about location and orientation, even though you didn't like densely sample all possible locations and orientations in the beginning.
Yeah. And one note about this is that it wouldn't really help us very much with the switching from one object to another. It just assumes that we just have the object in the same, we're just trying to refine the hypothesis space to go towards that same object. But because it's based on the absolute evidence scores, it's just not, it's relying on what it thinks that object is to sample new hypotheses. So once we switch from one object to another, that high evidence scores doesn't really mean anything. So it doesn't really help us get switch from one object to another. So it's not really geared towards compositional objects, but it's nice to have because it can make us recognize objects faster, which is something we might need with behaviors. So we might come back to it. So yeah, so this is the whole idea. Is just instead of resampling a large hypothesis space at the beginning based on that sensory information, we continue to refine the hypothesis space over time. At every step, we're doing this. And these are the results with resampling. So again, this is the same figure. We're switching between objects. And as we are switching, this is the maximum evidence scores. And we can see that we're able to switch from one object to another. And Monty is able to recognize these objects as we switch. So the evidence for, at least for the first episode, we're expecting it to do good. So it's accumulating evidence and everything. And then this is where the improvement is happening. Basically, the second object, it's accumulating. It now has hypothesis that it can accumulate evidence for the second object and then for the third object as well. So as we switch, we're able to switch Monty's recognition to the correct object. Now, for the theoretical limit, it also makes sense because the theoretical limit, even though it has increased as soon as we change the object from one to another, but then it continues to decrease as we resample more and more scores. And then even as we resample more and more hypotheses. And then even Monty is able to do good on these hypotheses because we now have hypotheses that we can accumulate evidence on. Then we're doing good for all of the objects, basically. Yeah, I think this is the last slide. This is a comparison on the benchmarks that we defined at the beginning, where we do not remove, we do not do the manual reset of Monty between episodes, and we ran the benchmarks. So we have no resampling and full resampling, and then also one thing that we're investigating now is using a smaller hypothesis space, which would make Monty faster, as you can see here. So the runtime experiment, when we're using a 70% of the hypothesis space, Monty can run faster because we're always refining that hypothesis space, and we're using a smaller hypothesis space. So Monty can run faster, and it does not affect the performance much. As you can see here, it's kind of like the same performance.
I thought, I'm confused about this. I thought that I would have, oh, I see. There's a third bar that's really low there.
Yeah.
I was gonna say, like,
Yeah, I was
I'm
gonna
gonna be
say.
the same. It doesn't make sense.
So
Okay.
I think you wouldn't have been at our kind of normal Monday meeting when Ramy first presented these results, but in kind of a very understatement of the century, I think he was like, "This is a nice improvement." But yeah, it's we basically go from 0% accuracy on this benchmark to close to 100%. So it's a huge jump.
Right.
So yeah, this figure actually shows two really key improvements. One is being able to solve switching between objects without any supervisory signal. And then the second is that now we can actually have a much smaller hypothesis space size. Before, if it wasn't in the hypothesis space on the first step, it wasn't possible to be recognized at any time during the experiment. But now, as we're resampling all the time, we don't have to have everything in our hypothesis space on the first step. So it seems like we can make the hypothesis space quite a bit smaller without much impact on the accuracy.
Yeah. I think my
question. So I realize the effects are small here, but I was just wondering if you could speculate as to why for the distant agent, the 70% size went down a little bit, and for the surface agent went up a little bit in terms of percent correct.
Yeah, so these are like I don't have any idea. Basically there is also one thing here with the runtime. Surface agent is running faster, which I also am not sure why. But so even without resampling, the surface agent is much faster, and this might already be also in the original benchmarks. So
I think that's just for the like the policy. It just converges faster because it explores the surface more efficiently.
Yeah, could be. Which means
so
also
like I guess that there was kind of a proportional decrease in the number of steps. That's what I'm pretty sure we've seen before.
Yeah, and we didn't get the improvement. Like, so here we have like a large improvement in the distant agent, but we didn't get that much improvement in the surface agent in terms of runtime. So yeah, these are things that I'm still looking at for wrapping up this project. I'm gonna go over the like an interactive visualization. It'll just take a few minutes, but it may make some things clear.
This is a new visualization that Ramy put together. That's really cool.
Thank you. Okay, this is on my other computer, so you'll be seeing my side of my face. So basically, this is the simulator. This is the ground truth of what Monty sees, and so we have just like we saw with the previous with these figures, we have the object that Monty is seeing in the simulator on top here. So it's going to see a strawberry and then a banana and then a mug and so on. And then this is the evidence of which object Monty thinks it's seeing over here. But then in the simulator view, that's what's actually happening in the simulator. And in the most likely hypothesis, it's basically plotting the maximum evidence over here. So as we move between these.
We're not seeing your cursor, I think. I'm not sure if you can turn on a laser pointer or something. Or just be a bit more descriptive in what you're pointing at.
Yeah.
Yeah, like maybe just highlight, I guess, in the simulator, Monty is the kind of red circle with and then the direction it's looking is that line. And then I'm not sure if you saw, Jeff, but there was like a green dot on the MLH side on the hypothesized object. And that's basically where Monty thinks it is on it.
I missed that. But we're just going to get to some comments I have in a moment here about attention. Is the green dot over there?
Yeah, you can see it just peeking around.
There it is. Okay, that was not visible to me. Okay.
Yeah, sorry, I'm not able to have the cursor shown. Not sure why.
Oh, it's all right. I think if you just say on the bottom you see X, then it'll be
right.
Yeah, I wasn't aware. So the bottom plot here, this is the one that we've seen before, and this is the Monty's evidence. And at the top of that chart, we also see which objects Monty is.
Talk about resampling and changing. I was thinking I was going to be looking at a cup. So this red blob thing that's a strange looking cup. It looks more like a strawberry, I think. But I'm trying to fit it, make a cup out of it. But oh, damn, it is a strawberry. You didn't
some
say
strong
that.
priors on your hypothesis space.
Right, because we were talking about cups the whole time, and I'm trying to make that damn thing a cup. And at some point I go, wait a second, there's a green thing on top. It's a strawberry. Of course, it's small on my display, and you zoomed in on it too. Okay, that's funny. I wasn't doing very well on my inference.
We do have a cup in Scott's new data set, so we can use cups in the future. It's just that cup. The Menta cup doesn't exist in the YCE data set, that's all.
That's all right. It's fine. It's just funny.
We have a mug over here.
Okay, it doesn't matter. Pick, but the strawberry is great.
Okay. So I was just showing what we're seeing is this is the agent, and this is what the agent is looking at.
This being the left,
right.
the pin looking thing.
In the simulator view, the red sphere is the agent position,
right,
and the black line is basically the what it's looking at. So this is the patches.
Yep.
And on the right view, we see in the most likely hypothesis, this is what Monty thinks the object it's looking at, what that object is, and also where the agent is or where the sensor is on the object, and that will be shown as a green sphere. So something like this, basically thinks this is the sensor.
Does that green dot represent the actual size of the sensor patch?
No,
That's because it's way too small, I would think, right?
It's so these experiments have noise in them. So even sometimes you will see on the right side that the patch location is not exactly on the surface, and the sphere is like
I'm just saying, I'm just trying to understand how much of the object is being sampled by this learning module or this sensor module.
Oh, right. So you can look at the whole experiment basically like from the beginning on the simulator object, on the simulator view on the top left. You can see how many steps it looks at.
I think he's just saying
I
there's
think
no-
Jeff's asking about the receptive field size. Maybe
Right.
if I share my screen, I can show you what it has been for other objects in the past, and then
That seems because that
it should be similar.
the green dot, it seems way too small of a sensor patch.
Yeah, it's larger than that. It's not. It's maybe, I don't know, like hard to describe. But
well-
yeah, Ramy, if you stop sharing for a second, thanks. Because
I mean,
yeah, this is
maybe
actually something we show in the paper. So, for example, with the mug, you can see you'll see like a kind of a
Right.
rim and just underneath, and just
I assume the red dot in that figure represents the size of the patch. I've always assumed that. Is that not true? Go
no.
back to the image you just showed.
So as in the patch is something more like this. So it's
Okay,
still pretty small.
Right, but it's bigger than what we just
It's
saw
not
a
a
moment
dot.
ago.
Yeah.
Right. I mean, because, all right, I mean, it's an important variable, the size of that patch. Obviously, the smaller it gets, the harder it is to learn and infer, and the more details you get, but it makes other things much more difficult.
Yeah, I think that'll be an interesting. I was just say that'll be an interesting thing to experiment a bit more with now that we're bringing compositionality and hierarchy, because then we can have like a higher level learning module have a larger receptive field.
Right.
Yeah. Was that for surface agent or distant agent, Ramy, on your visualization?
Destination.
Distant? Yeah.
Although what the sensor module sends to the learning module is just a pretty basic summary statistic. So it just sends the center location of the patch and the color at the center of the patch. And then the main thing that's influenced by the size of the patch is what kind of curvature is being extracted from locations in the patch. But it's still not saying anything about like how things are arranged within the patch or anything like that.
No, but I think it would, anything within that patch will get averaged out in terms of its curvature and
yeah.
right? And so you don't want to be modeling every single dimple of the strawberry.
Yeah, I just mean it's not like you get a whole lot more information into the learning module if the patch gets.
No, but I think it's helpful.
Smooth.
It's helpful for visualization to just imagine. I understand that, but it's confusing to me to look at and see that teeny little thing. It's like, okay, we're not really sampling that point. We're sampling an area around that, some area, and then that's otherwise you would learn the curvature of every in and out of every dimple if it was just,
Yeah.
right? You don't want that. So anyway, that would be helpful. I kind of remember it's the first time I ever thought about this, because in the papers and previously there's always been some sort of rectangle like Niels just showed, which said, oh yeah, there's the patch, and I can correlate that to the image that, this is what the patch is seeing. But here it doesn't look like that. Here it's just like there's a point. And you're using the size of the green dot as some sort of error, I guess. But that's a very different sort of representation than we had in the paper.
Yeah, that's an interesting. I think it would be useful to add like even just the RGB view of what it's looking at, or like a window here, like a square.
It would be, personally, you do what you need to do, but from my point of view, it would be helpful that green dot shows the area of the patch.
Or even the simulator, because I guess the patch only exists in reality on the left.
Right.
But yeah.
Well, okay. What? That doesn't make sense.
And just to clarify, I guess the green dot, I don't think its size varies I think it was
Oh, I
just
thought
it
it-
was
I thought
it was I think it was clipping into the mesh
I see.
because there's noise in the locations it receives. It's not going to like
Anyway,
if you take
it
its
is.
hypothesis and yeah. Anyways,
It just occurred to me right away. It's like, oh, we're moving the sensor of the object, and how much area of the object you're sensing on the sensor is an important variable, and it's missing here, so it's confusing.
yeah, no, that's a good point. I think it would be nice to visualize, and we could
And we
even
did
have like
that.
a yeah.
We did that in the paper figures, and therefore wasn't confused by it.
Yeah. Yeah, fair
Another
point.
quick question about that. You said it's the distant agent, and so like on the left, where we're seeing a dot and then a line,
Mhm.
like presumably the agent's quite a bit further away than where that dot is for a distant agent. So I'm wondering, is that just some fixed distance from where the observation was taken?
I'm not sure if it's much further away than that.
That's a fair
You're
point.
holding
Is
you're
it
holding the
possible
strawberry
it's a
really
surface
close to
agent?
your eye.
Yeah.
Like, oh, strawberry.
Scott found a great video of like these guys like studying t-shirts. I think we we should share it, but it's kind of the fever dream that Monty experiences. Um,
I mean, this distance doesn't really matter at this point. It's not a practical distance for like a vision system necessarily, but from a theory and implementation point, does it matter at all at this point? It didn't seem like it would.
Yeah, not really. I mean, I do think the Asian is probably a bit further away because the not zoomed in view, like the viewfinder, gets a full image of the strawberry, which seems difficult at that distance.
Mm.
But yeah, since it is kind of like a 10x zoomed in view for the patch that we send to the learning module, then
So yeah, I used the agent position, which didn't seem to be displaced by that much. Maybe it's something in like I can dig deeper and
maybe the camera just has a wide field of view or something.
it could be, but yeah,
Ram, I have a basic question for you. So you're talking, what we're doing about here is the lower learning module deciding, oh, I'm no longer on the mug and now I'm on the logo or something like that. And what about the upper learning module? It's ampling the same spaces, the same points. Why wouldn't it do the same thing?
I think this is the like having the stacked LMs on top of each other and both of them looking at this at the same observations. That's I think that's one of the things that we're still working on in terms of how to enable the
Okay, so it's an open
learning modules.
question.
Yeah, that's actually something we wanted to talk more about, maybe at one of the next research meetings, because I think we're all a bit unclear on that right now. Besides giving the higher one kind of a larger, lower resolution receptive.
Well, I have a lot of thoughts about this right now, so we don't have to wait.
Yeah, maybe Ramy can walk through this visualization first, and we can.
Right. I've been waiting, so I'll wait some more.
Okay, so it's just as we move the you can see that the line, the vertical line in the bottom figure, it moves as I change which step we're on, and as I move, and we're still looking at the strawberry. It has basically the most likely, as long as the most likely hypothesis is the same orientation and object as the simulator, then Monty has a good idea of what it's looking at. And then as soon as we switch the object to a banana, Monty still takes some time to delete the wrong hypothesis and refine the space. But after some time, it thinks maybe it's this different object, the Lego piece, and then maybe a mug or whatever, and then it thinks it's a banana, but it's in a different orientation, and it starts looking at different parts of the banana until it figures out the correct orientation. So same thing happens again with the mug. Let me just fix the orientation a little bit. And this is what it starts with, and then after some time it gets the mug, but then it thinks maybe it's a inverted mug. You can see that by looking at the opposite side. So it thinks the sensor is on the opposite side over here, which would make sense if the mug was inverted. And after it fixes that, we can see that it's now looking at the rim over here, and it thinks, yeah, I'm on the rim. And yeah, after some time, we get the same things with all the objects. So yeah, it's able. So in these figures, Monty is not getting any resets between the objects. It's able to switch between them and quickly decay the incorrect hypotheses. Yep. There is some interesting observation here with the mustard bulb, where it basically it thinks that it's 180 degrees rotated based on the observation that it sees, because it's looking at it from the side. So it's hasn't looked as much at the texture, like the barcode and all the text. It's looking at it from the side. So it thinks that it basically thinks that it's 180 degrees because it's symmetrical on that axis.
I imagine as well, if you looked at the hypotheses, the relative differences, the hypothesis for the symmetric rotation would be quite similar. So like,
Yep.
even though this is technically the most likely hypothesis, they're probably quite close.
And it would be very quick to change to it once it looks at any of the texture. Like if it sees red over here, it will be very quickly to switch to the other one where it has the
Right.
correct. So you can see that, yeah, it thinks it's a different orientation, but it's very close to it. Yeah, this is it.
Very nice visualizations.
Thanks, Jeff.
Yeah, it's beautiful to see also how kind of the rotation hypothesis quickly refines itself, and how even if it's wrong initially, it's wrong in like meaningful ways, like along axes of symmetry, because it hasn't seen the disambiguating evidence yet. So it's really nice.
Yeah, there were some places where it figures out that it's the right orientation once it looks at the discriminative features like a handle or the rim of the cup, and right after, like just a few steps after that, it just adjusts itself. Sometimes it just only takes one step. But it's also interesting to see that Monty figures out the correct goal state where it wants to be to basically disambiguate this the orientation. So that's also, it was interesting to see that it picks the right places to look at, like the handle of the cup or the rim.
Yeah, nice. Yeah, no, overall, this was all really nice work, both, yeah, with the hypothesis resampling. Awesome that could kind of solve that new benchmark. And then, yeah, I definitely agree that visualization is going to be really useful. Like even just the kind of the thing that Scott spotted, I think that's an interesting thing about, being really close. I just think it's going to be super useful for debugging, because like that might be, I think, actually partly from the jump to goal state where we have this desired distance. And I think I was just kind of using whatever the default parameter we had for the distant agent as well for that. But that might actually be closer than we want to be. We might want to kind of Jeff's point, to kind of like smooth out the sensory observations we're getting. So it might be something to revisit, and I'm sure there'll be other examples like that.
Yeah, I'll definitely look into it, just to make sure.
Yeah, it's also occurring to me that when you change the viewing distance, you are going to change the size of that, how big that receptive field falls on that object, as we were discussing. And if the stored model kind of assumes a certain kind of distance, like how the patch size fall over, then all of a sudden you're much closer and you're seeing a bigger part of that object. Then the amount of curvature, like how you estimate the curvature, could be pretty different because, you're sort of averaging over a larger area.
No, I feel like that's kind of the beauty of Monty, is that it shouldn't be too sensitive to that. I agree
Yeah.
that like, yeah, it might be unexpected, but in general, I think it's going to be very different from that same distributional shift. Again, if like a deep learning system saw that, where
Sure, yeah.
it's used to like this zoomed in view or vice versa. But yeah, I think
Honestly,
you're right.
it's surprising like that, it hasn't made any noticeable difference at all thus far. Like after a goal state is achieved and you're really close, it's like we don't see any noticeable like drop or in performance or whatever after that fact. So
Yeah, but it would be
already seems
interesting.
very
Maybe
robust too.
maybe it'd be better without it, or yeah, a bit further back. But yeah,
Ramy, yeah, I'm curious, have you had a chance to look if this improves performance on the normal noisy experiments? Because I think we kind of expected that maybe as a side effect because it removes the reliance on the first observation that might also be noisy.
Yeah, I'm still looking into that. I ran some experiments on the default benchmarks, and I have some weights and biases things to show, but there are some things with the pose error where I've seen the pose errors like increase on some of these experiments, and I'm debugging it just to make sure, like, because it doesn't make sense to be increasing. So that's one area I'm looking into.
I have a bunch of thoughts when we're ready.
yeah,
course.
I think
Could you bring up the mustard container again? To share your screen.
Yeah,
All right, just stop right there. That's good. Oops.
it's going to adjust.
All right, that's good. All right. So I have two general thoughts. I believe it feels very strongly to me that when we look at an object like this, so here's a mustard container and it has a bunch of stuff on it, that there actually is an event that occurs it's an attentional event that occurs when we want to focus on some part of this object. So it's not like like a V1 and V2 are just scanning over this thing, and V1 is just sort of by magically picking out logos and words, and V2 is magically picking out the whole object. It's like, for starters, both V1 and V2 would be looking at the entire inferring the entire object. And then you would attend to some part of it. And when you attend to that part of it, only V1 is attending to that part of it, and V2 is still looking at the whole thing. And I'll go into that a little bit more detail. Also, we have to keep in mind that ultimately in these systems, we're going to have many columns looking at these objects. So if I think about V1 and V2, the entire object is going to be somehow covered in V1 with many columns, and the entire object might be covered in V2 with many columns, regardless of whether the columns are representing the same size of receptive field or not. So we have to make sure that, so it's like when I would look at this mustard thing, I might say, oh, that's a mustard container. I actually don't read the words. I don't see the words until I attend to them. If I just flash that in front of me, imagine I just flashed this image in front of you. You'd say, oh, it's a mustard container. And then I say, well, what do the words say? You say, I have no idea. If I, on the other hand, put a little, and I've done this experiment, I put a little rectangle around the word Frenches. So now imagine all you see is the rectangle. And I say, I'm going to flash an image in front of you. I want you to attend to what's in the rectangle. And I'll flash that image. You'll see the word Frenches. You'll know, oh yeah, it says Frenches. The same exact input coming into the retina. I'm flashing I'm flashing this image, but I'm telling you in advance to attend to some part of it or not. And the retina gets the exact same impression. I can have the same fixation point. I don't even have to be fixated in the rectangle for the Frenches. I can be fixated anywhere. And you will see the word Frenches in one case, and you won't have any idea what it says in the other case. So this tells you that there's an attentional mechanism going on to break out a part of this image so that you infer what that part is. So when I think about looking at a compositional object like the cup with the logo, I imagine at first you actually, I know it feels a little weird. You actually don't see the logo. You see it's there in the same way I could, when I flash this image of the mustard container, you see that there's text, but you don't know what it is. You haven't really inferred the specific details of the child objects. It's sort of like there's a general morphology or a model of this thing, which includes sort of colored areas and so on. But the actual details of what's there, you have to attend to. So, so what I imagine the first time, like I'm holding, a coffee cup in front of me right now, and I say, oh, look, this is my cup. And then I say, oh, there's some text over here. I actually never noticed what that text says. I have to attend to it. And it says, oh, it says Copco. I could have seen it 100 times. My eyes could have actually fixated on those spots 100 times. I've never seen the word. It's only when I attend to it do I see the word. So I think there's an attentional mechanism that's required to do this. And that attentional mechanism is, in some sense, a reset, if you will. It says we're now going to attend to some subset of the input space. We're expecting to see something different than I was seeing before, which is the cup. Now expecting something else. This, by the way, the work you did, I think is really useful in general, but I think it's not sufficient to solve this problem. And so it just basically, I think when I look at an object with a composition object, I will first look at the whole thing, and then I'll start attending to details. Oh, what's over here? What's over here? What's over here? And each time I attend to the details, I infer a child object completely. And then somehow, the V2 is not attending to that subset. V2 is still representing the entire object, but only V1 would be attending to that subset. It seems to be something like that's necessary.
Yeah.
To do this.
Yeah, I feel like that's. Yeah, no, that's really interesting. I think it makes a lot of sense.
Also, we have many columns in V1, and some of them will be on the attended subset, and some of them won't. So we have to tell which ones we want to pay attention to, right? So
yeah, that was what I was going to ask. Was if that's kind of the main mechanism, most is like kind of windowing the area of voting.
Right, and it seems initially that this is a model-free process. It's like I don't know what. I don't know what there's a word that says Frenches. I don't know that says yellow or 40% or anything like that. I don't know that. There's somehow it says, oh, there's some stuff there. Let's attend to it and see what it is. And so it's not like these things are invisible to me without attention. It's just it's somehow in the overall model of the mustard container without the details of what the child object is. And again, since I don't know what the details are, it can't be a model-based attentional mechanism, at least not initially when I'm learning it, because I don't know what's there. It could be, it's more like, oh, there's a border of red, so maybe I'll tend to that, or there's a border of blue, or I'll tend to that, or there's some letters, and I'll tend to that. So I think this is what we're doing when we're looking, this is happening constantly every time we move our eyes. We're attending to different subsets of the world, and then we're assigning those subsets as a child to a larger portion of the world. And even V2 might be on the retina, there might be there are multiple objects, like you might have the coffee cup and the mustard container, and V2 is like attending to the subset, which is the mustard container, and V1 is then attending to the subset, which is the red. Now that I attend even closer, I see it's a flag. I didn't notice that before. See, I've been looking at it over and over again. I didn't know it was a flag. Now I attend to it more carefully, and I was attending to the word. I didn't see the flag, but then I tend to the red spot. I see it's a flag, but I don't really see the word. So I think this we have to have some kind of mechanism like this. And of course, when we do this, we are inferring. Often we just do this inference of the flag or the word using many columns that doesn't require movement or very little movement. So I can just quickly attend to the red area and say, oh, it says Frenches, or attend to the word says 40%. I don't have to like scan over it. I would if I had a single column. So we'll have to be thinking about multiple columns voting to infer the word Frenches, or then infer the word 40%, or the word yellow, or something like that, or the flag. And so those are the two things I think we have to add to what you've done. I think we're going to have to add this sort of attentional window, which initially is going to be somehow model-free. And then we have to make sure that we're able to, coincident with that, be able to have multiple columns voting on that. So a real system is very, very quick. I just recognize the logo in one flash. I know that logo, bam, because multiple columns voted on it. I know the word Frenches because I've seen that before. Multiple columns vote on it.
Could it be that we reset based on confidence or prediction error? I think this is something that I've been discussing with Niels and Vivian.
Prediction error of what?
So if you move to a different place or attend to a different place and you have a prediction of something there, then this is, and it's not there, then you start resetting, or you sample very quickly, like sample more aggressively.
Maybe. I certainly that seems to occur in some situations. Obviously, Um, I'll show you something funny. I'll be right back. 2 seconds.
Yeah, I mean, in some sense, your slope
Here's
tracker
a-
is a prediction error. But sorry.
I thought you guys might enjoy this. Can you see this? You can see my mic here? Maybe get myself view up here.
If you hold it higher.
Okay, here we go. So I took this to the my talk last week, and I got home. I noticed something immediately jumped right out at me. I don't know if you can see that. It's chipped.
Whoa.
So it's a nice chip. It's really a nice
Yeah,
chip. So it's almost like I'd like to have a cup like this, because now I can use it as a. It didn't break the whole cup. It just made this perfect little chip.
Yeah, it's quite satisfied. Normally, it's off the surface and it's kind of ugly. That's more like that's weird. It looks almost like a cut.
It didn't, though. If you see the inside, you can see it. I actually had the piece. I could glue it in, but I don't want to. So anyway, my point is that's a prediction error, right? I think. Because if I had this cup all the time, and this is the cup I used every day, I'd take it out of my bag and I wouldn't think anything about it. We'd just say, yeah, that's the cup. You get used to it, right? Your model gets modified. But the first time I see it, it's like a prediction error. This is what On Intelligence, the book, was all about. So I think there is an issue of, but I'm not sure. Yeah, I mean, in some sense, in this prediction error, it says there's like a new feature on this mug that I didn't see before somehow. But I think it's the morphology model that's messed up. I don't know.
Yeah, I think
So
the prediction error will be important in general, but for the kind of attentional mechanism, it's more about gating which inputs we're actually giving to the learning module to infer the object.
right,
Gating
right.
it
In
to
fact,
only give the red parts of the flag, or to only give the French lettering.
right. In fact, and we have to be thinking about multiple columns getting that gating, right? So which we're basically saying there's an area of the, I'm not sure if it's the area of the retina or an area of the space in the world. But we're giving it an area that says we need to attend to this area and ignore everything else. And what do you infer in that area?
Yeah, it
And
almost
now,
seems like that kind of ties into what we were thinking about part of Scott's work, which is like, this is like explicitly motor attention, so only moving your eyes in a certain area, but basically having like a model-free policy that makes sure you stay on a child object until you recognize it. So basically only saccading within the French
right.
Um,
It might be a little bit more, maybe I don't recognize it right away. And maybe it's a compositional object itself, like the flag plus the word that I hadn't seen before. So you have to you'll spend some time in that little area exploring, building up models of that, and then you can pop out again.
Yeah, and it's nice how
Yeah.
the same sort of model-free mask or whatever could inform voting as much as it can inform the policy. So that we
Right.
can still get it to work with more of a sequential thing, but it would
I'm
work
not-
even better with voting.
Right. Now, if obviously it seems like once I've learned, if I really study this French's mustard container, then maybe I'm not sure if the attentional mask would be model based or not. I don't know, but initially it can't be. So
Yeah, I think we were thinking that, yeah, like you say, initially it would be model free, but then like model based would probably be really useful for things like robustness to clutter and things like that. That like, I'm pretty sure I can see like a chair behind that other, that table or whatever. And so you have a hypothesis of a chair, and
right.
that kind
You
of
would-
gives you
you
some sense of
somehow-
where it is in space.
Right. In
Um,
fact, when I think more about that, it feels like attentional mechanisms are you're attending to an area in space, not an area on the retina. It feels like you're tending to a depth in space and an area that's exposed. And I don't know how that happens. I don't know how the brain does that, but that seems like what it's doing. We could start with attention to an area of the retina or the area of the receptive, the array of sensor modules. But somehow it seems like it's more than that in brains. Somehow brains are able to say, I'm attending to that table, which is about 10 feet away, and I got something right in front of my eyes, which is partially blocking the table. I don't see it at all. It's just I'm not attending to it. It's like, pay no attention to the things that are not 10 feet away. It's like weird.
Yeah, I think the things you're bringing up, like everything you brought up in the last 5 minutes is like a lot of intense debate in the RFC that I'm working on about all of these issues. Like you basically identified like a big section of the kinds of issues that we've been talking about. like including like whether or not this is we're attending in retinal space versus like world space, you know. So yeah, we've been
Yeah.
it ties into this other RFC really nicely.
So, if great. Well, I hope I'm not being redundant then.
No,
No.
I think I think the nice thing is it's fitting with, I think, what we were biased towards doing. But
Right,
Yeah.
but
right.
I think you're also bringing up stuff that we haven't, you're definitely bringing up stuff we haven't talked about, like voting and using the same attention mechanism for
Right.
voting, which I
So
think
yeah,
would be quite easy to extend and would be a nice
right.
adjustment.
I mean-
Conceptually. Go ahead, Ramy.
Yeah, just that we haven't really conceptualized it as attention so far. We've been talking about it as policies, which I feel like thinking of it as attention is a bit more general in the sense that we can also apply it at the high level modules that might not be influencing the policy as much, and we can use it much more broadly. So yeah.
Hey, it just occurred to me, given our distance sensor, which has it has distance built into it, right? We could do attending to volumes in space, right?
Yeah, that's
Yeah,
what we're
and
doing.
so that's what we were kind of thinking of doing, and it would make it easier, because one thing we were thinking about, and this is maybe starting to segue into the next discussion, is like how you combine, let's say, what your model-free attention or kind of sensory input is telling you to look at with your model-based one. And that's much easier, actually, if they are both working in space rather than in retinal coordinates.
Right.
Because then
right.
your eye is telling you, oh, whoa, there was like a loud noise over there. And your model-based thing is saying, oh, well, someone's doing machinery or whatever, and those will match in the space that they're talking about without actually working in 3D space. If you're trying to do in retinal coordinates or some binaural kind of auditory coordinates or something like that, it's much harder to kind of get them to work together.
Well, that's great. So, I mean, in biology with eyes, it's much trickier to attend to space. You have to use various sort of binocular clues and as we've talked about, and also the parallax issues and things like that. But given the kind of senses we have, it could be much easier to do it. So I think let's combine this together. I think this is Ramy, this is great work you did. I think we have to, and I think it's going to be useful all around. And just general inference. It's like we have to decide whether we want a new object or not. But I think to solve the compositional object problem, we have to assume that two regions are attending to different things. One is tending to a larger object, and one's tending to a smaller object. But they're both, you can have to assume they're both multi-learning module arrays, and they're both getting, in some sense, the same input. We don't have to assume that V2 is getting larger receptor fields than V1. That's not an assumption and a requirement. And therefore, V1 has to attend to some volume in space or some point in space that V2 is not attending to. And therefore, and then with the multi-columns, we can infer that sub-child object very quickly. And so, in the ultimate system with Monty's running around the world doing things, they're going to be just like us. They're going to be going, oh, that's there, this there, that's there, and building up these models as they go.
Yeah, I think that's a nice way. Like, the nice thing about thinking of it as attention is we can apply a different mask to the lower level learning module than we apply to the higher level module. So if we want the lower one to infer the logo, we can gate that we only send observations within a certain area in space, and then the higher level one can get observations in a larger area of space. So that's that's really
that's the first time I realized this now, that I think both V2 and V1 both have to have their own attentional spaces. They both have to be attending. So in some sense, maybe that's a general principle that's going on all the time. That of course, if I give you a blank screen and I say fixate on some point and I show you an image, you wouldn't know where to attend. I don't know what you would do. Maybe you'd attend to everything, but very quickly you're saying, oh, this V2 is attending to the mug, and V1 is tending to the volume of the logo, and then V2 is attending to the logo, and V1 is attending to the letter, that kind of thing.
A question about that. Could the higher region be initiating the attention for the lower region?
Well, that would be a model-based attentional mechanism, right? And we talked about, I guess, sure, it could, but I don't think it can initially.
Yeah, that would be kind of after we've learned the compositional object, almost like in the backward connections, maybe. Or just generally, if we have learned a compositional object, we know where the child object should exist. So that would be easy information to use to, well,
Yeah.
one, predict the child object, but also know which area to attend to.
So if we're looking for some child object somewhere, that's where the higher region can initiate that attention. But we're also talking about model-free attention, which cannot be initiated from high region.
Yeah, I think that makes sense.
I'm gonna stop sharing.
Yeah, thanks, Ramy. Yeah, so this feels like a nice transition into, unless you had other stuff you wanted to talk about, Jeff, into the next part, because yeah, basically we've been talking about bringing in kind of more of these model-free policies to kind of tell us how to move to attend to things or to stay in an area of interest, and that's kind of raised these questions of like, how do we kind of coordinate that with these kind of model-free attention / kind of policy signals with model-based ones,
So
and kind of
just
leading to this.
the interaction between model-free and model-based action policy,
Yeah.
is that what you're saying?
Yeah, and this is kind of leading to this idea of having something like whether it's kind of the basal ganglia or a mixture of kind of subcortical structures, a sort of like goal state or action selector that's kind of receiving these and then telling the motor system ultimately like, okay, this is what we should do.
Well, is this due for inference or due for doing like a task, goal-oriented task and so on?
So right now, I guess it would be focused on inference. Yeah, so it's not going to be a complex like hierarchical task. It'd more be like, you are typing at your laptop, and generally you're kind of relying on your model based kind of signals for that. But then something kind of falls over, and you kind of then attend to that, or you are kind of walking while talking to someone. So like there's kind of a bit of a bottleneck of how much can actually be done, and potentially there's kind of a system there that's sort of saying, okay, these are the things we're going to sort of prioritize and actually allow to happen.
It's really about picking where to attend to next.
Yeah, at this point, yeah, it's.
So you're going to present some work on this, or are we just discussing this?
Yeah, so we don't have any work on this. This is basically something we were planning on working on, but we just thought it'd be useful to get your feedback before we get too far with it. And it's particularly been something Scott's been kind of brainstorming on.
It clearly there's we've talked about this multiple times that model-free attentional mechanisms are really hard to resist. It's like I've talked about the classroom where you tell all the kids to look at the whiteboard and say, don't take your eyes off the whiteboard. And then someone opens the door on the side of the room and everybody's heads turn. It's just like, it's unstoppable in some sense. It's really, really hard. So there's this, clearly this in some situations, unexpected behaviors. Now, maybe it's just in the periphery. Maybe it's an evolutionary argument that says, animals are about to attack you from the side. So when you see movement on the side of your periphery, you have to attend to it. I don't know if it's a general mechanism or not, but there are certain cases where the model-free attention is dominant and hard to overcome.
But yeah, it feels kind of like it's a scale, and it can sort of vary, because you can also, except for the most extreme kind of model-free signals, it feels like you can also kind of block it off. Like if we say, for example, a model-free signal is prominent colors on the screen to sort of catch your eye, and things like that. That's something that if you are just kind of seeing a new scene and you're curious about it, you're going to kind of let those signals take over and kind of follow them. But equally, if you're trying to do a task-oriented thing, you're going to block all that off, and you're not going to let that drive you.
It reminds me, I go to some websites that are just filled with ads and videos and little things popping up all over the place. And of course, in Firefox, I don't know about other browsers, there's a little tab you can click. It's basically gets rid of all that stuff, and all you see is the text of the website. Like, it's like I have real trouble not paying attention or not being annoyed or not. It's like a struggle to fight to not pay attention to all that crap that's going on in the periphery. And it's such a relief when it all goes away and you can just read the text. I'm just showing as an example of it can be difficult in situations where you know that stuff is extraneous, you know you don't have to pay attention to it. It's a challenge to just tune it out. And that's how advertising works, I guess.
Yeah, I think maybe it makes sense if Scott kind of goes through the basic proposal and like.
Oh, so you have a proposal?
Yeah, there are
Okay.
like two mechanisms we're kind of thinking about right now. One is saliency based, and one is kind of a bit more like defining the region of interest to stay within. Like what's all.
Sure. Okay, that's
one
great.
object.
Great.
So
Great,
yeah,
great.
I don't know, Scott, if you have like some slides or just the pictures from the RFC.
Can I go fill up my coffee cup again?
Yeah.
Anyone else want to take a?
Yeah, should we take a quick break?
I'll take a cup, thanks.
All right, a couple minutes.
Okay, so gonna present our this RFC about model-free and model-based policies, and so I guess just a very quick.
Have you heard the term RFC, Jeff?
It's request for commitment. How about that?
Comment. Yeah,
Comment.
it's just like a kind of
It's
a
like
proposal.
Proposal to I want to do something to the code base, and we get to somebody vets it.
Yeah.
I thought you guys vet it. See, you're
We
proposing.
do. Yeah. So like here's the RFC, and you can see like how many comments there are. Like everybody weighs in basically, and you make adjustments and
Right. If you guys want me to look at this, let me know. But generally, I'm not looking
I
at these
can
things.
drop in like a human readable version of this into the
No,
Slack if you like
you don't have to. If you want me to be a commenter on these things, fine.
Sure.
If you don't mind it doing it this way, it's easier for me.
Okay.
Whatever works.
So it's a little non-obvious how this is related to compositional objects, because this proposal kind of has some new architecture that seems sort of generic or useful in many situations. But sort of the top level idea is that at first we were thinking something like a superior calculus. So you're able to take sort of a wider, coarser field of view and maybe use that to identify, like they say, the label area on a child object, and that somehow, based on these sort of model-free signals, you can choose to attend to like the label area and stay within it. And that's the idea, sort of like the very coarse-grained idea behind this RFC. And
this is just what we were just talking about this, right? Pretty much.
Exactly,
right?
yeah.
Yeah.
So this RFC proposes a couple new items to fold into, like a couple new classes to fold into the code base to help support this. So I guess I could have a version here of Monty without the proposed pieces, but normally we have observations of a cup or whatever, and they go into sensor module, which then goes straight into a learning module. And then the learning module can emit goal states. It doesn't have this goal state selector. And so the model-based
I don't know
goal.
what a goal state. I don't know what a goal state selector is. If I need to know what that is,
I'll introduce in a second. I just
Okay.
realizing maybe it would have been helpful here to have a version without the components, the added
it doesn't
components. But
It's all right.
normally there's no goal state selector. This learning module just goes straight to the motor system, which can either execute sort of model-based things when they're requested model-based actions, or otherwise just sort of take control and do model-free actions.
We have, correct me if I'm wrong, today we have no model-based action policies, is that right?
That's not true. The
Oh, no?
hypothesis testing policy.
Oh,
is
right.
model-based.
You're right. I'm sorry. Totally shouldn't.
That's right. And but
Spoons versus forks.
right, exactly. And right now, when that comes through, that always takes over. So like, it's almost the opposite of, I guess, what you were describing before, of like certain model-free signals always will cause you to.
Well, a model-based policy for inference is going to be better than a model-free policy for inference. I guess the earlier we were talking about a model-free policy for like totally look at something else, stop what you're
Yeah,
doing
and
and do
that's
something
why I
else.
feel like I think it's not going to be black and white. I think we'll want situations where
Right.
we generally rely on model-based signals, but there are going to be situations where a model-free thing kind of will break through
Right,
the sort of
right,
attentional window and say like, look, this is really important.
Right, okay.
Yeah, and as Scott kind of said, that what he's going to propose is like a pretty general solution. So we started with a specific problem we want to solve, but I think we settled on a really nice general solution that will solve a whole bunch of problems. For example, also right now, the model-free policies are kind of happening within the data loader and the motor system. So there's like a bunch of sensor processing happening in places that shouldn't really be doing the sensory processing. And that's kind of one of the things that Tristan has also been working on.
Well, I guess it's going to be
Kind of
outside of the model. So where do you put it is the question, right?
Yeah, so that's what
You-
Scott's gonna.
Right. So you're suggesting it shouldn't be in the sensor module. It should be someplace else. Is
Oh
that
no,
what
I'm suggesting it shouldn't be in the motor system or in the data loader. It should be in the sensor module.
Oh, okay. I mean, I don't have a good sense what the data loader is, but fine.
Like we don't want sensor processing to be happening in the motor system.
Okay.
Yeah, so this proposal adds two new items. Here's the salience map sensor module, name subject to change, but that's what we have it called so far. And then something to help sort of manage the combine. So this thing generates model-free states, the salience map. It's sort of our stand-in for superior calculus in the sense that it just takes in, we expect it to make salience maps, perhaps some very primitive types of segmentation, or at least segmentation within the visual fields to maybe help you stay within a label area, some constrained area.
Of course, there's a lot of work on salience maps and vision, and I'm not up on it, but it seemed like it was sort of, it wasn't clear cut, like, oh yeah, these are absolutely happening all the time, or where it says, oh, maybe it's a poor explanation of what's going on. So I'm just pointing out there's a lot of research on this
Yeah.
as to whether these things really exist or not. But it's okay idea.
Yeah, and
Yeah.
I think one thing, just while we're on this topic, was interesting. From a brief look at the literature, there were people arguing that at least at some point in kind of the caliculi and stuff like that, these saliencies are in kind of a 3D, more kind of egocentric rather than retinotopic coordinate space. Again, because of this problem of like, even if it's all model free, how do you combine signals from audition and vision in terms of telling you
Right.
where to attend? And it seems like the superior and inferior caliculi can do that. And so it would make sense that they're doing that in some shared space. So,
Right,
I mean,
right.
like you were saying earlier, I mean, maybe it doesn't matter so much for us because we can get 3D very early on, but it's just kind of nice that might not be too crazy from a biological perspective either.
No, that's not at all. Okay. Okay.
And maybe just to clarify that this is just a different type of sensor module, which I think is like one of the things I really like about this proposal, that originally we thought about introducing a whole new component to Monty, which is kind of like a subcortical sensor processing area. But then kind of realized that this is something that we have sensor modules for. And basically the only change is that sensor modules can emit goal states as well. And those will be kind of locations to attend to that were picked based on model-free criteria.
Okay, so these are, I mean, you can call them a sensor module, but they're not, they don't feed into a learning module, right? They're outside of the.
No, but they receive raw sensory input.
Right,
So
right.
they have that kind of thing in common. And then their output, like the earlier sensor modules, is also in the CMP format, because the goal state is a CMP signal. It's a location and pose in space.
It's a location pose
with potentially other information about it.
It's a location in space.
But it's definitely a location.
It can't have a pose and it can't have an ID because it's model free. So
yeah,
so
well, it brings up some interesting thing. We were thinking maybe there could be something kind of like a model-free ID, which is like really just like a temporary kind of like there's this stuff, which is this ID, and there's this stuff, which is this ID. I have no idea what these objects are. I'm not going to learn about them or model them, but I'm just telling you that I think this is different from that.
Well,
And
maybe,
in,
but
in that sense,
calling
there
it,
might,
calling it, as
yeah,
soon as you use the word ID, I think
right,
it has to be a model. I
right,
mean, there could be a subcortical model, right? There are, you know, it's been shown
like an
that, like, you
evolutionary
know,
thing.
even, you know, humans have this sort of thing that subcortical that sort of detects shapes of snakes, you know. It's not a really, it's a, you know, very crude sort of long thing that wiggles a certain way, and that's built into your genes.
Right.
So you can have some sort of models down there, but they have to be very crude. It can't be anything specific. But the general assumption, I mean, it even could be learned. Well, the reason I like this, I think, if we think about Monty as basically learning modules and sensor modules, and there's this common architecture, this whole separate path you're proposing here is sort of independent in some ways. I mean, it could work any way you want it to work, right? It could be, you know, signal from the internet saying, you know, go look in the hallway down here. I mean, I don't know. It's just sort of a separate system that says you need to pay attention to something over here, and how it actually works should be independent of how learning modules and sensor modules work. Is that correct? Seems like.
Yeah.
I think that's fair. I think it was just it was a kind of conscious decision or a kind of realization to have the output of this be goal states as well, because
Well, again, maybe
be locations
let's
in space,
define a
because
goal
we
state.
felt like that
If it's a
would enable
location
them to work together.
if it's in a location in egocentric space, I'm all into that. I think that has to be that. What else could it be?
Yeah.
Right? But that's got to be what it is. Now, if that's what you mean by goal state, fine.
Yeah.
I'm still struggling with that word, so we'll have to get into it a bit more, exactly what goal states are.
And it is still an evolving thing. I think unlike the other ones, the other CMP signals, we've sometimes said it can be a bit less defined, as in like some of the features or kind of properties are optional, but I think location always has to be there. And so in that sense, it fits, I think, with this.
Right. So it's a separate sort of, I mean, it's right. We have to figure out the mechanism for this, what you call the salience map in this diagram, but it's really anything that we want to use a model-free attentional space detector, and then how it interacts with learning modules, or how it interacts with the model-based action policies.
Yeah, but I wouldn't say it's independent of sensor modules. So at least how Finn think why I like it is because it's basically it is a sensor module. So like we still have sensor modules, learning modules, and motor system, and the sensor modules are responsible for turning like raw sensor information into the CMP and do the sensor processing. Only now we're giving the sensor module the capability to send messages to the motor system directly instead of to the learning module, and then the
Well, I think they should be separate sensor modules. If you want to call it a sensor module, it should be separate. For example, I may be looking at something and I hear a sound, and I'll turn my head to the direction where that sound occurred, and behind me or off to the side. So it doesn't have to do anything at all with what the sensor module is actually sensing at this moment in time. That's the one that's being fed into the learning module.
Yeah, but your sensor that's detecting sounds can at any time also send the sounds to learning modules. But then if there's
maybe not.
Maybe
not. I mean, I'm arguing the opposite. I'm saying you could think of it independent of that and saying, like, you know, I might be an animal that actually doesn't understand sounds at all, but have a really good vision system, but the sounds could still be very useful for me for attentional mechanisms.
Yeah, I mean, there's no requirement that you send it to a learning module, but
Right.
I don't
So
see
why
why a sensor module wouldn't be able to send its messages to learning modules.
It could be, but I guess the trick is you don't want people to think that sensor modules that send signals, you could combine these two things in a single module, but conceptually they're not combined. Conceptually they're different. So don't want to fool people to think that a sensor module has to do both, because it may not. Like, I don't know if a touch sensor, surface sensor, really has an equivalent to this. You know,
I think
mean,
it would, like feeling something hot, or I
Right,
feel like
but
a sensor module that is disconnected from cortex would be like the enteric nervous system in the GI like tract. Like
let's go back to vision. Imagine I have a vision system with a single a learning module and a single sensor module. So it's just like looking through the straw. My attentional mechanism is always going to be bigger than that. It's going to take the entire retina, and it's going to be looking for movements or something like that in everywhere in the receptive fields. So it's like that is a sort of independent sensor ability than a single sensor module, and that's the same thing that's going on with touch. I mean, I could in touch I could have an unexpected temperature, but generally when I, you know, if I have a single touch sensor and it's moving over an object, the idea that if I feel a bite on my arm and I recoil from it, that's a different system altogether. It may be combined with a single sensor patch, a patch of skin, but it's almost certainly different actual sensors in the skin.
Yeah, so that's why we kind of drew the saliency map SM to get this large receptive field as input. But also, I don't see a problem why this large receptive field SM couldn't send something to a learning module, or why a small receptive field sensor module couldn't send something to the motor system, like for small adjustive kind of microsaccades or something like that. So,
well, I guess I know it seems like you want to combine these. I think I would just caution against that. I mean, I don't know. You know, if I feel a sharp pain in my, like a bite on my arm, I'm not sure that is a useful signal to send into a learning module. I would want to attend to it visually. I would also recoil from that. My body would automatically recoil and move away from that.
yeah, those are more reflexes, right?
Right,
Like
but these are
safety
things.
guards. Like
Right,
that's another category of things.
right. So I'm just saying I could take all that stuff and put into this bucket of, you know, outside the cortex, model-free action policies. And they can be all kinds of things. It could be reflex reactions. I could have new sensory modalities that only work for these attentional mechanisms. Like, as I said, I could hear something even if I don't understand sounds. I like the idea of separating them and treating them as differently, although whatever it is still going to send in a location signal into the motor system.
I mean, I think like reflex reactions are kind of different, but maybe mostly because they wouldn't go through the goal state selector. They wouldn't really compete with any other signals because they are like safety guards, reflexes that you have to perform no matter what else is going on. But then,
and I think those don't use a location or send a location. Those actually directly tie into a muscle contraction.
Right, but if I feel a bite on my arm, I will automatically move away from it. But I will also automatically.
That's like a more primitive reflex.
Right, but I'll also automatically turn my eyes to look at that location, and I'll turn my head and my eyes, and I'll visually attend to that spot. So they'll do those both simultaneously.
Right. I mean, for what it's worth, I'm not sure how important the distinction is at this point, in that, like, I feel from a code perspective, it makes sense to call it a sensor module and just communication perspective, because it takes in raw sensory input and it's outputting a CMP signal.
I just don't want, I think it's okay. I think that's great. I just think when people are trying to learn about Monty, they have to understand it's not like other sensor modules. It's different. It can sometimes play a similar role, but it's really it's serving a different purpose in some sense, and it doesn't have to be tied to that modality. It doesn't have to. It could have different. Everything about it could be different than a typical sensor module. So
I think even if it shares some commonalities with the sensor module, or a lot of commonalities, we can definitely introduce it, you know, to users and things like that in such a way that makes it seem pretty distinct, even if we later on say, oh, by the way, under the hood, a lot of this is basically the same as a sensor module.
I like that approach. I mean, you could just call it something like an attentional sensor module, or you know, pick some term that just differentiates it, so you know this is a different class of sensor module. And And if it works on the same CMP principles, and that's great. But it really is, you know, it's different in many ways that we just talked about.
Yeah.
I mean, yeah, I don't know. In my head, it's still not like categorically different. It seems kind of like a continuous shift between like when is the receptive field large enough for it to be an attentional one versus too small to be one. Like it seems like kind of a continuous. I don't see like
It's like it's
where the
you know,
clear
in
cut is.
a human, every part of our skin is tuned to this. There isn't a single part of our skin that can't, under the certain type of sensation, the different sensors. These are sensors that might be pain, heat, sharpness. Those sensors are a completely different sensory system that covers our entire body, and they're active all the time. And in vision, the entire visual field, including the periphery, is active all the time. You can't attend away from it for these purposes. So in that sense, they seem different to me. They're sort of very large global things that are occurring. Well, look, I think Scott proposed, what's wrong with just calling it something else, calling it an attentional sensor module? And then we can see if it makes sense to feed them into a learning module.
You know, actually, so this might actually sort of support the point you're making. But we were talking about having this sensor module produce potentially lots of goal states.
Can we just say, what is a goal state? Is that a point in space to attend to? What is
It's a point in space to attend to, yeah.
Like move my center patch here. Is that what a goal
Yeah.
state is? Okay.
Whatever it takes.
It can be
yeah.
more than that, at least as we've conceptualized in the past, but that's what it is as a minimum.
Right. Well, I think it should do that. It should generate that. I mean, that's the idea that I feel a bite on my arm and my visual system will immediately attend to that location in 3D body space or 3D world space. So yes, it is. It has to generate that.
Yeah. So we don't necessarily want the regular sensor modules to be doing all the work of emitting lots of goal states out here if they're not going to be used, if they're just going straight to a sensor module. So I suppose just having some way to maintain a separation in the sense that, you know, there's a lot of work here that we don't need to be doing all the time for these guys that this one would need to be doing.
Yeah, I mean, how I was thinking of it is that sensor modules, basically the same as learning modules, can have a goal state generator. And if a sensor module isn't wired up to connect to the motor system, or isn't getting a large receptive field, or we don't want it to generate goal states, it doesn't have a goal state generator, or it just has a very primitive goal state generator that only emits goal states if there's like a sharp pain or something. But then the same.
What for saliency? That's also a goal state.
Yeah.
Isn't it?
So that one would have a pretty.
When would the salience model, salience sensor not generate a goal state?
No, yeah, that one would for sure have a goal state generator, and that one would be rather complex and processing the whole kind of visual field that it gets as input to determine the goal states. So like our current sensor modules that feed into the learning modules wouldn't necessarily need to have a goal state generator, but then the one that's like responsible for the attention would for sure need one, but might not need as much other sensory processing machinery that we have in the regular sensor modules.
One
Right.
thing.
So
Go ahead, Jeff.
no, you, Tristan.
One thing about the code organization, like I know that in a goal state selector, like these goal states, these Model-Bsaed goal states coming from this sensor module with goal state generator, they're privileged and they're being pulled apart, and the goal state selector needs, like what I've seen in RFC is it is able to distinguish between them. And so that would be a case for calling it something else, like a attention state or something else. If we're gonna a priori say these are distinct from what learning modules send because the goal state selector can't tell them apart, it could be so like another proposal could be it's an attentional state. Maybe it has two modes. One where it's like advisory, and the other one is, once you get to the reflexes, maybe there's attentional states that have to do that you can't ignore. But like this could be advisory attentional state or something like that. But then to another argument of this might be something different is that maybe it's like maybe looking at from the goal state selector, having to tell these apart might also be a relevant framing to think about.
Well, I don't see why you couldn't tell them apart. I mean, basically, you could say that the saliency attention sensor may not be active all the time. I mean, so if it is like the pain sensor would be, but like in a visual saliency feature detector, maybe if it's happening in superior colliculus, for example, doesn't have to always be producing a saliency detect. It could only under certain conditions it could do that. But when it does, and then you would attend to it. I'm just saying you could always give preference to the saliency sensor module, but the saliency sensor module doesn't always have to be outputting something.
Yeah, I think generally the goal state selector wouldn't necessarily need to know where the goal states came from. It can just select based on kind of the confidence or the relevance that the sender gives to that message.
Well, I feel like there would be, because as in, for example, it might treat, or it would probably treat model-free and model-based signals differently. But I don't think that's unreasonable
it
doesn't have to, but I feel like, yeah, it doesn't have to, but I don't think it would be unreasonable from a kind of neuroscience point of view, because obviously some of these inputs are coming from hardwired connections from subcortical structures. Some of these inputs are coming from cortex. So those are very different things coming across very different axons. And so it's not hard for those to be treated differently.
But it doesn't need to be told that. It can just learn that certain signals are more reliable than others.
Well, I don't know. I mean, there's two ways you could do this, right? You could pass in some sort of confidence. And so based on the confidence, the goal state selector would figure out what to do. Or you could allow the saliency generator to make that decision, right? And say, well, I don't think this is important enough to tell you about, so I'm not going to tell you about it. Or this is really important, you should do it, or something like that. Those are two ways of doing it. I personally like the latter. I think you like the former, Vivian. But you could work both ways. I feel like it just feels to me like cleaner to just burden the saliency detector. And so like Monty in its current form, model-based is really clean. And then it generates goal states. And then we can build this other little system on the side. It's very embodiment dependent and sensor dependent and almost task dependent system to say, okay, well, how much do we care about pain? How much do we care about unusual things? How much do we care about whatever? I don't know. There's two ways you could do it: and burden the saliency sensor, or provide confidence. I don't know if one is inherently better.
Yeah, I think we need a combination of both. Like the saliency one shouldn't output thousands of those and have the goal state selector do all the work. But then again, there should also be some kind of confidence. Like if there is a very salient signal, sharp pain or something, it would be sent with like kind of an alarm signal attached to it. To the
well, it feels like, imagine the saliency in the classic view, which was like, oh, there's some high frequency components in this visual image over here. Right? So go look at that. Something's interesting over there. That's when I think about classic saliency. And then there is a separate thing like, oh, there's pain on your arm over here. Go look at that. Those are really separate systems, I suppose. And they're not really it's not one thing. It's like those are separate saliency kind of signals that come in and have different priorities.
But I guess it would be nice, just for simplicity, to kind of try and put those just on like a spectrum within, like, yeah, I agree. Maybe you need different kind of, as you were saying earlier, like task specific things that are like detecting looming is like a very primitive reflex that, small mammals have and stuff like that. like a looming shadow. And so I guess that's a hardwired thing that's separate from detecting like yeah, as you say, like high frequency textures.
Right. So
But from the point of view of the goal state selector, if it's all just signals with like various levels of kind of confidence, and then it's just some can really scream out, look, you need to act on me now.
okay, I think you could, right. So you could do both. You could have a confidence signal coming in, but it has to be able to say, you know, maybe we're going to build some robot construction workers for Mars, and they don't care about shadows looming. They don't care. There's no predators, you know, just ignore that. So
Hopefully on Mars.
you know,
No.
yeah, that's right. Hopefully, aliens. Whereas, you know, a biological animal, that's important. I like the idea of saying, okay, we have this system called Monty. It models the world, and now under different situations, different embodiments, different tasks, different sensor types of things, you have to provide these saliency signals, and some of them would be graded like maybe like the high frequency visual components, and you know, like where to attend visually. And some of them would be like binary, like danger, pain, you know, something like that. And as long as the system can handle that variation, clearly in a way that doesn't really impact the models in Monty, then I think we're okay. I mean, it's like leave this up to the designer of the system to come up with any kind of saliency thing they care about. It doesn't really impact the way learning modules and sensor modules work, the general sensor module work.
Yes, I think it's both options are available to us in the future. We can kind of just try the really simple confidence-based thing and kind of work in a more separate stream if that seems. I think there's still just kind of a lot of open questions in the RFC.
Well, you could do it all with the
yeah.
confidence based. Just let some sensor modules be able to just force their way and say, I get 100%, you have to do this.
Yeah.
And other ones would be like, hey, you know, right over here, you might want to look at this. Maybe you don't, maybe you do.
Yeah, I mean, I think I was originally kind of thinking about it as separate, but you know, for just kind of a first pass, since I'll be, you know, the one implementing it, I thought, oh, maybe we'll just do the confidence thing first, because it also has like the nice property that like it just makes things simple for the goal state selector. It means
fine, confidence is good as long as you allow someone to have a binary choice. You know, there's no, you know, like this must be done.
Yeah, so it's almost like confidence is scaled from 0 to 1, but you can also send inf. And if you send infinity, then that one will always get acted on.
You need to have that ability. And by the way, even something like vision, you might have multiple vision sensors that do saliency. You know, you could have ones that are detecting motion in periphery. You could have other ones that are detecting, you know, spatial frequencies nearby where you're looking, within the object's boundaries that you're looking at. So those are really separate types of ideas. They're not really one thing. So now that we're talking, I never thought about this before. So this is all new to me. You guys have been thinking about this, but now that I'm thinking about it, it seems to me like, oh, there's all these different systems that come into play here, and they're very much application, embodiment, sensor specific, task specific almost. So we have to have a lot of flexibility for someone to come along. Just like in embodiment in sensors, we have a lot of choices what you're going to use. You have a lot of choices about, as a system designer, what you care about in terms of these saliency sensors.
Yeah.
Are you happy with that, Vivian? You seemed unhappy about it.
No, I'm happy with that.
Okay.
Yeah.
Does that make sense, everybody?
Yeah, and I mean the goal state selector, maybe we don't really need to talk about it too much now, and it's something I think we can leave this to the future. But yeah, I've just been thinking about kind of how much sort of hardwired intelligence we also want to put here in like a model-free sense still, but in terms of how it decides to kind of like, yeah, the simplest thing is basically it just gets all these confidence signals and it just picks the maximum one. But if it's something like, oh, I want to pay attention to this part of the world, or I don't know. I probably just need to think more about it before I can propose anything. But yeah, it just feels like there might be some greater complexity there, and that might map onto something like the basal ganglia.
Right. I think also, just as we were talking earlier, the goal state selector should really be an area of interest selector. I mean, a volume of interest selector, something like that. It's really not a point, like we talked about you're tending to some volumetric space in some sense.
Right.
And that we might want to start thinking about the goal state selector that way. It would still work for a single learning module, and as long as the sensor module lands inside of that space and the sensing in that volume, it'll work. But then if there's multiple learning modules in parallel, we want to care about which ones are sensing in that volume. All of them have to, there's a bunch of them in that volume. So just maybe expanding the idea of goal state selector to a goal, I don't know, volume selector.
Yeah, I think that's
Yeah.
what we tried to show here with like some of the circles also being bigger, like the learning module could say attend to this broader area in space, and then based on kind of saliency within that area in the feature space, it would then pick a certain spot, specific spot. But like, yeah, I don't think
But that would just generalize that to it's always picking a volume of space.
yeah.
And at any point in time, it could change its volume to be bigger or smaller, depending on its needs.
Yeah. Yeah.
Well,
Yeah.
it seems,
This.
yeah, the
Oh,
motor
sorry, go ahead,
system eventually has to move to a specific spot. But
Yeah, that's an interesting question, right? How, if I'm, let's say I'm moving a bunch of sensors, like on the retina, or a bunch of sensors on my skin, and I, 2 fingers, I want them all moving to some volume of space. I don't know, what does that signal look like? I don't know. It's like, oh, move all of these to this area. Each one's getting a different one, different location in that space. It's interesting.
Yeah, I think part of the way we were thinking about it was a combination of things. One is you can, have a set of goal states, so they can, in some sense, kind of tile space. But then also you can have kind of, as well as confidence, you can sort of have like a blurriness, or almost like a Gaussian kind of like around a location, and that can be smaller or larger. So you can say like, I really want to attend to this exact location in space, or you can say, yeah, look approximately over here. And that also applies to like, if you need to place an object in an environment, sometimes you care about a location very closely. Sometimes it just needs to approximately be satisfied.
Well, I don't know about that. The more I think about it, the more I feel like it's always a volume, and your volume can get so small that it looks like it's a point, but it's always a volume.
Yeah, okay. I guess it's never a mathematical point, but yeah.
Yeah, I want to put this cup.
I
want to put this cup on top of the trivet on my desk here, right? Well, that's not that is an area of the trivet matching an area of the cup. It's like it's not like a point on the cup and a point on the trivet. It's like,
yeah, and even if you're threading a needle, which is probably about as precise as humans can do, there's an eye. It's not like a single point, I guess.
Right. It reminds me, I saw this exhibit in this really freaky museum in LA, and they had all these really curio type of things. And someone had made these sculptures, 3D sculptures of individuals that all fit within the eye of needles. And so there was the Pope, and there was Elvis. These tiny little things, they're so microscopic. You need a microscope to see them. So even the space of a needle can have a lot of detail. It was called the Museum of Jurassic Technology. It's definitely worth seeing. Okay.
Just that when we're talking about the goal state and kind of what it could do, that reminded me. Yeah, one thing we were talking about is maybe giving it definitely like a short-term trace, a bit like a short-term memory, but just of kind of where it's attended to in the past, so that it can kind of bias itself not to go back there.
Right. I think the literature in vision shows that too, right?
Right.
I think there's some sort of inhibition of previous saliency
inhibition
points.
of return. Yeah.
I don't know what it's called, but I already looked over here. Now look someplace else. Don't look there again. So again, that will all be in the algorithm of the saliency detector, I would think. Not in the model. It's a model-free parameter. It's a model-free decision.
Right.
Yeah, I love
Okay,
doing
nice.
it that way,
It
because
sounds
then
like
you can we just burden the saliency sensor module of all this stuff that we don't want to think about right now.
okay. So that one you reckon the traces in the saliency detector, because it doesn't actually know what we've attended to. The goal state selector knows what we've attended to. So it feels like it'd be easier to do it in the goal state selector. Because all the saliency ones are going to be sending lots of different signals, but the
Well, I
goal
don't
state
know.
selector
Well,
could say like, okay, well I went here. Let's try somewhere new.
well, I don't know. I could make the argument either way. It feels like something that's independent. It's model free, right? It's really model free.
Definitely, and the goal state selector is model free, and any
Okay,
decisions it
well
makes.
then it could
I
be
mean,
in the goal
it
state.
can be
Yeah.
informed by goal states
Oh, it
that are
should.
model based coming from the learning modules, but it
But
itself it's
but
model
you
free.
want the saliency detector to say, don't keep sending me the same thing, because I know I already saw that. So
That's interesting. Yeah, that could also maybe be like a recurrent inhibition or something. Like it could say like,
I don't know.
Well,
yeah.
doesn't
So
the
if-
sensor module know where it looked at? That's how it can get information,
Well,
right?
Niels is arguing that the sensor module, the real sensor module knows what it looked at, right? But the saliency sensor, I'm
I
arguing
mean, I think that's a fair point, Tristan. Yeah, that it could get that from that. Yeah,
Yeah.
somebody has to know it. So I don't really
Right.
care as long as it's not in the model system.
Yeah, I
Right.
think Tristan makes a good point. It should know it, just based on the sensory input it gets. It should actually know it better than the goal state selector, because maybe the motor system failed in executing the goal state.
True. Yeah, that's a good point.
I guess I guess no, it should be fine. Because the sensor module would also have a sense of 3D space. I was just thinking if the sensor module, because it's going to be outputting in 3D
I don't think,
space.
well, the
'Cause
sensor
it
module,
basically it needs to map, like after it moves, obviously its direct input is going to change. So it needs to somehow kind of solve that correspondence between what it suggested attending to before and what it's seeing now. But yeah, as long as that's like in 3D space, which the output at least is, then
it's
could do
pretty
that.
complicated. If you look at someone saccading, looking at a face, it might go back and forth between the eyes and multiple times over again. Or eyes, nose, mouth, eyes, nose, mouth, eyes, nose, mouth. So it's not like, oh, I look there, don't look again.
Yeah.
It's more complicated
Yeah.
than that.
So I
Yeah,
was
I'm
planning
sure we
on
can tune it.
I was planning on encoding like the don't return here, not so much as not sending goal states for areas that you've been to, but more just like reducing that confidence value by just like, so my bias was towards sending a good amount of goal states, locations to look at, and the confidence values can just essentially be weighted at some point or another by how recently you visited. But it would be up to the goal state selector in the way I conceived it to perform that weighting, though it could be done in the Salience map SM. But that is the decision to reweight goal states and confidence and things like that is something that could be sort of like a component of the system that can be sort of plug in, like modular,
I
I
guess
suppose.
the way to
So-
go ahead with this, and maybe this is a burden on Tristan or somebody, I don't know, but the way to go ahead with this is just give ourselves lots of flexibility here, because it's clear we haven't thought through all the issues. And we want to be able to rapidly in the future try different attention mechanisms and so
Yeah.
on. And people may even need to do those experimentation and final implementations. So let's not make sure whatever we code, we don't code anything that restricts us in the future of moving these things around and trying different strategies on them.
For
Yeah.
sure.
That's
Yeah,
the
that
best
makes
I
sense.
could suggest right now. It just
Yeah,
seems like
that's
we're just
fine.
making this up right now. We don't really know enough. But
Right. But
Yeah, I guess another point or consideration here is like we don't know what users are going to want to build for like whatever they make for a Salience map SM or something. So I suppose from a sort of extensibility side.
Well, you're right, and that's the same with the sensor module, right? We don't know what
Yeah,
sensors are going to use.
exactly. Like
So, I mean,
try not to hard code in too many decisions.
I
That
mean, I
can't
think that's
easily
the
be.
beauty of the Monty architecture. You know, it has these learning modules which are really generic. You're going to be the same in theory, close to the same no matter what. And then you have these sensor modules which are have this non-generic interface to the world and a generic interface to the learning module. So
Mhm.
the same thing would be, we want the same with these saliency sensors, that they have some common interface to the goal state selector or the attentional volume selector, whatever it is. And then people can futz around with them all they want and change the confidence and change the how they work, and you know,
Yeah,
all
that's
kind of.
why I like thinking of the saliency map SM as just another sensor module that generally sensor modules, you can attach a goal state generator to it, you can connect them to the motor system or to the learning module or both. You have all this flexibility. You don't have to do any of it, but basically code-wise, we allow sensor modules to directly send messages to the goal state generator.
But if the saliency sensor, I don't see any point where it ever would send a signal directly to the learning module.
And you don't have to, but maybe someone has a use case, like maybe
Well, okay, but let's be
smaller-
careful.
maybe you have a small receptive field sensor module like we have today that sends messages to the learning module, but maybe you still want to use that to perform some microsaccades to kind of adjust to exactly the specific feature in that small
So-
patch.
I think that's fine. Just in the documentation and the description, people could get really confused. And so I think that's saying that you're going to have the saliency thing sending directly to a learning module is a corner case we haven't actually figured out yet. And so I would just don't talk about it right away, you know, just because it's hard. These are really hard concepts. And so I think that'll confuse people. But if mechanistically fine, right, I don't have no problems with that.
Cool. I think, yeah, this was really helpful because I think overall it's encouraging. It sounds like, yeah, you're on board with kind of what we had been kind of thinking about. And I think it's just because it is a bit of a new kind of shift in terms of how we structure it. We just thought it would be worth getting your
Right.
thoughts.
You know, we're going to have to go through a very similar type of exercise when we talk about these model-based behaviors, right? We've touched on this before. There's going to be very specific elements of it that are not generic to learning modules. And, you know, they have to do with embodiments and specific features of embodiments. And so we're going to go through a similar sort of exercise in terms of motor generation. So again, Cortex is Cortex, and all this stuff below it, we'll have to pick and choose the stuff we want to do. That's fun discussion. I'm glad we're thinking about these things.
Yeah. Thanks for sharing that, Scott.
Yeah.
Nice. Well, I guess that's good timing unless there's anything else.
Did-
I can present if you want.
Oh,
Remember, I said I had some thoughts.
yeah. Okay. Yeah. Sorry. I had forgotten.
You don't have to.
But
you
I
don't
know
have-
that would be nice.
All right.
Yeah.
So I need to share my screen. So I guess that's good enough here. And then I'm gonna go
Just for kind of in case anyone has meetings and stuff. How long do you think?
Oh, I thought our meetings went beyond 10 o'clock now.
They can, but more as in like if people who are kind of maybe not on the research team want to stick around, I guess they just have a sense for how much longer we
The
might be
basic
talking.
ideas can be presented in just a few minutes. How much time you want to talk about it, that's a separate question.
Okay,
Um,
cool.
Okay, can you see my screen? You see my yes or no?
Yes.
Yes.
Okay, so it's just a Word document. It's labeled goal learning behaviors. So I want to think about start to think about the overall problem of, you know, having a system, you know, do your laundry, make coffee, build buildings, you know, whatever it has to do, assemble IKEA furniture. how would I even think about this problem? How do I even begin putting myself in a frame of mind to think about the problem? So these are just some thoughts along those directions, okay? So I'm calling that goal-oriented behavior. That's what I mean by goal-oriented behavior. Like, yeah, we want this thing to really work and do something in the world. And then I said, well, how do I even, what's the language of this problem? How do I, so anyway, that's what I started thinking about. So it starts with the models, right? Everything starts with the models and what they represent, because the goals, if we want to specify a goal to a system, it has to be expressed in the language of the models, because that's the only thing the models understand. So the goals have to be in the language of the representations in each learning module, because that's the language we can talk to the system in. So I say goals and tasks must be expressed in the language of models. In other words, goals have to relate to representations found in a column. That's just a general statement. It's like, I can't ask it to do something that the learning module has no language for. The solutions are similarly restricted. The solutions are restricted to the language of the models. If the model doesn't represent something, we can't ask the solution to come up with some other way of doing it. This doesn't mean that there still will be model-free motor policies and so on, but when we're talking about these goal-oriented behaviors, we're talking about things that are based on the model. So this is a very simple statement, but it helps me think about it. Think like, okay, well, what things can I express to a column to tell it I want you to do something? Then I said, in this paragraph, I say, well, one way to tackle this problem, is to define a base set of goal-oriented tasks that aren't very interesting in their own right, but these will be combined to solve real-world problems. In some sense, it's like, what are all the things a column can do? And then how do I turn those into a behavior? Right? It's like, so it's the inverse of what columns learn and columns understand. It's inverse in the sense, you'll see in a moment, that I want to take, okay, we understand how a column learns sequences. How can a column generate sequences? That kind of thing. So these are some of the items that I've come up with. The first one here, you can see, if you see my cursor, we know how to infer the pose of an object to its sensor. So something I might ask a column to do is move an object to have a desired pose to the sensor. Right? It's somehow, I don't know how to do this yet, but this is something reasonable to ask a column to do. And a column has the knowledge to do this. And so I can say, well, how would it generate behaviors to do this task? Similarly, I could say an inference task is infer a pose of an object to the body. We're not really, this is something I know brains do. And so the goal task here would be move an object to have a desired pose to a body, which is similar to the sensor, but not exactly the same. Another one might be infer the pose of a child object to a parent. And now the inverse of that would be to move an object to have a desired pose to a parent. Reorient this to fix the orientation of the silverware on the place setting type of thing. We also know how we're working on an inference task of infer the behavior of an object. So we can recognize the behavior, learn and recognize it. Now the goal task would be to cause a desired behavior to occur on an object. So I'm flipping around saying, I've observed this, now I want to make it happen. Another one would be infer high order sequences like melodies or object behaviors, could be high order sequences. And the goal task would be to create that desired sequence, the high order sequence, make the melody or make the thing swim or run, that kind of thing. Another might be infer, the inference task would be to infer an object ID, and inverse of that would be find an object with the desired ID. Like instead of saying, what is this ID, saying, here's an ID, go find it. Where is it in the world? So this is not a comprehensive list. It's not really, I said here, I made this quickly, like I wrote this last night. So it's in an order of like 20 minutes. So it's not a lot of thought went into this. But I felt like this is a way for me to at least start thinking about the problem. Like we should be able to do all these things. There's these base, elements of behavior where, and then we can string them together. Okay, I can stop talking.
I think that matches well with what we think we discussed this at like a brainstorming 2 years or 1 year ago or something, and we talked about goal-oriented behavior. And I think that's when we came up with the term goal state, which we used because basically it's the same format as the internal state of the column. So the internal state would be like, or what the column outputs to the next column. So that would be like detected object ID, detected object pose, detected behavior, detected sequence. And the goal inverse of that would be desired object ID, desired object pose. So basically, if you send a goal state to a column, you tell it, all right, I want you to do something so that whatever you're detecting matches this goal state. So
Right. I know
yeah.
these ideas, we've had these ideas around for a while, but they weren't crystal in my head before. That to me, like, it's like, oh yeah, sure, I could, on apical dendrites, I can specify, what my desired location would be, or I can specify my desired ID. But what I haven't done, so if this is repetitive, then it is, that's me. That's how I work. I didn't really said I could tackle these one at a time, like asking, how would layer 5A cells do this? I mean, I have to move here. Every one of these things requires movement in the world. Every one of these things requires some physical movement. It's not intentional mechanisms here. And so, and that connection I've never done. I've never really asked, how would the column generate a signal in its layer 5 cells, which is a movement vector, to achieve these individual tasks.
Yeah, I think that's an interesting. Yeah, if I'm understanding it, I think that part is new. That like the kind of the suggestion that there's a potentially finite list of sort of goal-like primitives that uses the language of goal states as we've kind of described before, and yeah, requires on you can only operate within a model that's known, like that we've discussed before, but kind of the suggestion that maybe there's this finite list that gives us the expressiveness we need to do pretty much anything.
Right. I started thinking about some simple tasks. I was thinking like, what if I had a bolt and a nut and I want to screw the nut onto the bolt? That's really complicated. I have to find these parts. I have to align them relative to each other. I have to know that there's a behavior that's related to threads and a screw. All these things and then I said like, wow, how do I start? Where do I begin? I said, well, let's just break it down. So we could call these like goal states, but to me, breaking them into these little atomic pieces is very helpful for me to think about. And
Yeah,
so
that's
the point of this conversation.
I think it's interesting. I think it does give me some clarity in that, like, I think often, like, for example, the hypothesis testing policy, we obviously implemented kind of like this. It was just like, this is a primitive where we're like, okay, sometimes a column wants to tell it's the most likely things it's sensing apart. And so it might have this kind of primitive for it. On the other spectrum was the idea of kind of like behaviors, and that, obviously a lot of tasks are going to be dependent on the behaviors of the world. And so you would learn behaviors, and then you would, informed by those behaviors, know how to act. But
right. But we never
but I
made
like
that.
the
We
idea
never
that
we never
maybe
connected those. Like,
and that kind of, so obviously behaviors can be essentially arbitrarily complex, but that maybe on top of behaviors there is this kind of set of relatively simple finite list of sort of subroutine.
right. I think to me this is the way of breaking it down into these components, because we have to be able to do all of these under different complex goal-oriented behaviors. And so then I'm thinking like, okay, well, column, once it can do these base ones, you just combine them in different ways somehow. But they have to be able to do these. So this thing, I always talk like, like the logo on the coffee cup, it's an example that exposes lots of problems. And so to me, this it gives me something to shoot for. Like, okay, well, how can I have no idea yet, but how can a column somehow move an object to have a desired pose? How does it do that? I don't know yet, but at least I know it has to do it. So it's a problem that I can sink my teeth into.
It's also interesting because
I feel like the history of Monty has been like, you know, we started off not having things implemented at a very neural level, and then we've always been like, let's see how far we can get without that, because it's easier to debug, easier to understand. But of course, there would be long-term benefits to having a system that's fully interpretable and doesn't have a bunch of neural elements. And those, again, are everything from interpretation to safety and all this kind of stuff. So, but it always felt to me like, yeah, once we get to this kind of stuff, it would probably become this fuzzy learning stuff that we
Maybe I'm not, Niels,
but
I'm not
but
suggesting.
I like the idea that maybe we don't need to well, it can be a bit more kind of hard coded, and it would almost be like, yeah, whether it's kind of neural links that like certainly some of these you could imagine how it's like, oh yeah, this is L5 projecting to this layer, and that's what causes a sequence to happen, and this is L5 projecting to this layer, and that's what causes a particular ID to be realized, or yeah.
Well, it doesn't have to be neural, the solutions. It helps me to understand the solutions. But by thinking about the neuroscience, I think like, oh, these layer 5 cells, they're almost certainly representing movement vectors in at least in the modules we have today, movement vectors starting out in the reference frame of the object, and you get converted to the reference frame of the sensor, the orientation. So how we implement it doesn't have to be neurons. I mean, but that's the base element. You've got a movement vector, and that's going to be because I'm pretty sure that's what the layer 5 cells represent. So I was confused about your comment about neuroscience. I don't think we have to. This doesn't have to be a neural solution, but
it's a. I'm just saying it's a positive. I think if we can come up with a list and then implement that without having to start having less understandable representations like neurons with Hebbian weights.
Right. Well, or we don't want to apply some sort of deep learning algorithm on top of these things.
Yeah,
if that's what you're saying. No, we really should be able to completely understand, like, okay, if a column, the only thing a column can do is output some sort of movement vector, and that movement vector is going to be learned based on the movement inputs it has received in the past. So it's learning to model. It basically learns what movements exist in the world related to its sensor, and now it is able to generate those movements. How do you solve these problems? How do you do these individual parts? Anyway, I think as we get into this, we're going to find all kinds of interesting complications and challenges. But personally, this is now, I feel like, oh, I can sink my teeth into these things. I now know where to begin with my own personal exploration. We're thinking about high-level tasks like making coffee and folding laundry. It's not base enough. It wasn't. I need to decompose it into the atoms of movement, the atoms of behavior, and then we can rebuild it up later.
Yeah.
And
anyway, I feel like at least some of them, when we've kind of thought about it, it feels like a nice thing is it feels like, again, kind of just simple associations can do a surprising amount. Like, the kind of light switch example of like a lamp or whatever, that you like, when you learn that behavior, you attended to a particular location, the state of the lamp, the switch changed, sorry, and then the state of the lamp changed. Like, we need to work out the details, but it's not too crazy to imagine that you kind of move into a location in a behavioral sequence and you see, oh, the light switch was in this orientation, but right now in the real world, it's in this other orientation. Now just output a goal state to kind of invert that or whatever.
right.
And yeah, I don't know.
Yeah.
That feels encouraging that it's.
So I was telling Vivian the other day, I said, well, I want to have all the theoretical constraints of Monty done within like a year, like all these things, and these big theoretical ideas. And so, to my mind, this is like this is the big area. To me personally, maybe not to you guys, but to me personally, this is the area like I have no idea where to begin. And I have good ideas about compositionality. I have good ideas about attention. I have good ideas about sequences. you know, we came up with some great ideas together about behaviors of objects. And so this thing has been looming in the background, like, oh my God, how are we going to start thinking about how to make a pot of coffee, you know? And you've broken it down, Neil, but it wasn't broken down the way I could think about it. So I feel like, okay, we're starting something that might take a year. So, or if we're lucky, but we should be able to do this. So anyway, I just don't want to over promise. I'm just saying this is the beginning of how to think about this problem.
Right.
Yeah,
No,
I
I
mean,
think
it's
that's
like
definitely helpful.
it's the last big open question, I guess, like after object behaviors.
I
So
still feel like there's abstract spaces is maybe the final.
Yeah, you know,
Yeah.
I keep,
But hopefully it's simpler than we
I
think.
think, Niels, I keep thinking like somehow that'll become obvious along the way. So as opposed to focusing on it, because again, I have no way of really attacking that right now. So don't worry about it. You know, cortical columns are cortical columns. Mountcastle seems to be right. So somehow let's keep doing the things we know we have to do. And maybe that abstract stuff will just fall out. I think it
yeah,
will.
it seems like it has to, because it should just be a matter of columns getting different kinds of input instead of having to add another piece of machinery to the column itself.
Right.
Right.
And
Yeah,
maybe,
it's just somehow where does that abstract movement come from? But
I
you're
don't know,
probably
but
right.
you
It
know,
probably is fairly. It's probably going to be something quite simple, just like representations changing. That's movement, or
yeah, I don't know. I don't know. I'm not too worried about it, but I'm not worried about it at all, actually. It's more of an annoyance, like, oh shit, we got to figure that out sometime.
Right.
But it's not going to require like, oh, we have to introduce quantum effects to, you know, to the sensor module, and you know,
I think
that kind of thing.
one thing that I also find encouraging, and yeah, it's just become more clear with like the recent papers and stuff, is like just how much can be done with kind of associative learning, because I think it's so common in, you know, machine learning or anything, that like anytime you don't understand something, you try and reach for these, you know, deep learning or whatever kind of a complex system that's going to learn how to solve that for you. But of course, when we actually look at how neurons learn, you know, it's some variant of just associative connections. But so we've gotten so far relying on that. So that seems encouraging, that the rest of, even if a lot of it's inscrutable, the rest of it will be the same, that we can, yeah. But
It'll happen. We'll figure it out. You know, and if we design robots and building houses on Mars and they don't have deep thoughts about philosophy, well, it'll be okay.
fair point. Yeah.